Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on random signal theory. In the previous lectures and the previous videos, we have been talking about random experiments. So, the main concept that we were talking about is the random experiment, an experiment that, if you do, gives you an uncertain outcome. So, the outcome that you obtain from this experiment is not certain. We talked also about the sample space, the set which contains all possible outcomes of a random experiment. We talked about events, and the event is a subset of the sample space of a random experiment. And then we also went through the basic operations that we can do over sets or events, like the intersection, the union, the complement, and the set difference. However, we have not started talking about probabilities themselves. If we have a random experiment, that random experiment comes with a sample space which contains all possible outcomes of this random experiment, and each of these outcomes occurs or happens with a certain probability. Now, in this lecture, we will start learning how to calculate these probabilities, the probabilities of outcomes of a random experiment.
First of all, what is the interpretation of probability? What is the meaning of probability? Basically, we can say that probabilities are used to quantify the likelihood or chance of certain outcomes of a random experiment to occur. Like if you do a random experiment, like if you take this course, we have talked about this example before. If you take a course, then the outcomes of this random experiment is AB plus C, C plus, and so on until F. Now, what is the probability of each one of these outcomes? Of course, this may depend on the student, depend on how much effort the student puts. But in general, if you have a random experiment that comes with a sample space, items or outcomes in this sample space happen with certain probabilities that reflect the likelihood or chance each one of these outcomes has to occur. In many contexts, the probability is used to represent the risk or uncertainty in engineering applications. Like if we have a machine, what is the probability that the machine fails? Or how long does it take? What is the probability that the machine fails after a certain number of hours? So all this is basically a reflection of risk in engineering systems or uncertainty, like in finance and similar applications as well. Probability can be used to interpret degree of belief, our degree of belief. How much do we believe in this outcome? Let's say, what is the probability that it will rain today in the afternoon? So when we talk about the probability of raining, it's basically the degree, how much do we believe that it will rain? So these are all meanings or interpretations of probability. Now let's go straight to business and start with the simplest case. If we have a sample space that consists of n possible outcomes that are all equally likely, we know in advance, we know from the nature of the random experiment that all outcomes in our sample space have the same probability. We know they have the same probability. Like when we toss a fair coin. A fair coin is a perfect coin, so the weight of each side is exactly the same. We know that if we toss, the probability of getting a head or probability of getting a tail, it's the same. Or if you roll a fair die that has faces from 1 to 6, again for a perfect die, fair, the weight is all equal, the weight is all balanced. We know that the probability of getting a 1 is the same as the probability of getting a 2, and this is what we mean by equally likely outcomes. So if we have a sample space that contains n equally likely outcomes, I don't think it's hard for you to realize that the probability of each outcome is 1 over n. Okay, to avoid just talking abstractly like this, let's see some examples. So let's turn to my own notes here and talk about a couple of examples. Let's say we have an experiment in which we roll a fair die. We have a die, uh, we have a die, and it's fair. So the outcomes, basically the faces, have all the same probabilities, and we know that the sample space of rolling a fair die, the sample space contains 1, 2, 3, 4, 5, 6. That's the sample space. This is what we have seen last time. But today, in this new lecture, we can also assign probabilities to each outcome of the sample space. We can assign probabilities, like we know that the probability of the 1 is 1 over 6, the probability of the 2 is 1 over 6, and so on. The probability of each one of these outcomes is 1 over 6. Why is that true? We just apply this rule. We have 6 outcomes in the sample space, and we know that each one has the same probability as every other. We know that these outcomes are equally likely, and we have 6 of them, so the probability of each is simply 1 over 6. A simple example that we don't have here is basically if we toss a coin. The coin has two faces, heads and tails. If we toss a coin, then the sample space contains heads and tails. And we know that it's equally likely because the coin is fair, so the probability of each one of these two outcomes, the probability of the head is a half, and the probability of the tail is a half. A little bit more advanced, we toss two coins here in this example. We toss two fair coins. The coins are fair. So each face has exactly the same probability, and we know that already from the nature of the experiment. So we toss two fair coins, and we observe the outcome. From the previous lecture or the previous video, we know that the sample space of this experiment is heads, 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 tails, tails, heads, and tails, tails. So we have 4 outcomes. Now, what can we add today in this lecture? We can basically assign probabilities of each one of these outcomes. What's the probability that we get 2 heads? What's the probability that the first coin is a head and the second coin is a tail? What's the probability that the first coin is a tail and the second is a head? What's the probability that both coins are tails? All these probabilities are the same, and we know that from the nature of the experiment, because both coins are fair. And since we have 4 outcomes, then the probability of each outcome is simply 1 over 4. So each one of these outcomes has a probability of 1 over 4. So basically, we started calculating probabilities already. We have a very simple case in which our sample space has n outcomes. We have seen examples n is equal to 6 or n is equal to 4, or in the case if we have only one coin, n is equal to 2. And as long as the outcomes are equally likely, as long as each outcome has the same probability as any other outcome, then the probability of each is 1 over n. Let's take it a step further. So we have seen some examples in which we talk about the probability of outcomes in a sample space. The probability of outcomes. What is the probability of head-head? It is 1 over 4. What is the probability of getting a 6 if you roll a die? It is 1 over 6. Can we also talk about the probability of an event? Let's try to remember the event. So that's why I have my own slide here, my own notes. Let's go back to the experiment that we mentioned before. We toss 2 coins and observe the outcome. The sample space has the 4 famous outcomes: heads, 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 tails, tails, heads, and tails, tails. Let's define an event, and we call it E. As we mentioned last time, this is the event. Just in this example, because we could have several events that we can talk about. In this example, the event E is the event of obtaining at least 1 head. Now you toss 2 coins, which means that you can get one of these 4, and you're interested in the event of obtaining at least 1 head. At least 1 means 1 or more. على الأقل, at least means 1 or more. So how can we express this event? This event contains heads, 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 tails, and tails, heads, because all these outcomes have 1 or 2 heads. These 2 have 1 head, this has 2 head, but the tail is not included in the event because we don't have a head here if both coins give you a tail. Now, what is the probability that this event happens? In other words, or in plain English, what is the probability, if you toss 2 coins, what is the probability of obtaining at least 1 head? What is the probability of obtaining 1 or 2 heads? It is the probability of this event. And here in this slide, we simply say that if we have a discrete sample space, if the sample space is discrete, like this sample space in which we can just count the outcomes, and this is just the opposite of a continuous sample space, which looks like a continuous range of values. If you have a discrete sample space, the probability of an event E, and let's denote it as the probability of the event E, equals to the sum of the probabilities of the outcomes in the events. Let me go back here. We expressed this event as having 3 outcomes: heads, 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 tails, and tails, heads. What's the probability of the event? It is the sum of the probabilities of the outcomes. So it is the probability of HH plus the probability of HT plus the probability of TH. And since each one of them was 1 over 4, so the probability of the event is simply 3 over 4. So as you have noticed, we express probabilities as fractions between 0 and 1. And we can also express it as a percentage. So the 3 over 4 is the same as 75%. That's how we can express probability. So this is the probability of an event if as long as the event is discrete. To get the probability of the event, we just simply add the probabilities of the outcomes that make up our event. Let's look at a more general example on the same concept here. In this example, we say a random experiment can result in one of the outcomes A, B, C, D. So regardless of the meaning of this random experiment, it's a random experiment in which the outcomes are A, B, C, or D. So if you do the experiment, one of these outcomes will happen. And it's also given in the question that these outcomes occur or happen with probabilities 0.1, 0.3, 0.5, and 0.1 respectively. So the probability for outcome A is 0.1, the probability for outcome B is 0.3, and so on. The probability for outcome D is 0.1. Now let's define some events. We use capital letters for events, so let uppercase A denote the event that contains A and B, just given in the question. Event A contains AB. Event B contains BCD. Event C contains only D. And now we would like to calculate some probabilities. What is the probability of event A? Now, the sample space and all the events are discrete. We can point here, we can count. It's not a continuous range. It's obviously a discrete sample space and discrete events. So to get the probability of the event, we just add the probabilities of the individual outcomes. So the probability of event capital A is the probability of A plus the probability of B. So 0.1 plus 0.3 is 0.4. Likewise, the probability of event B is the probability of B plus C plus D. So 0.3 plus 0.5 plus 0.1, which is 0.9. Now, event C contains only one outcome, little d. So the probability of C is simply the probability of little d, which is 0.1. Now, if we would like to get some other things. Now, imagine in this question, we also want to calculate the probability of A complement, the complement of event A. We still did not learn any formulas for probabilities, but here in this question, the events are given explicitly. We know that this is event A. So event A has A and B. So what is A complement? What is the complement of this event? Complement means not in A, which means C and D, the others in the sample space, but not in A. So A complement contains CD. And B complement here, if B is BCD, then B complement is A. This A is not in B. And finally, C complement, I don't have it here, but C complement, if C contains only D, what is C complement? Obviously, A, B, and C, right? So if we would like to get the probability of A complement, we get it from here. We know that A complement contains C and D, right? So what's the probability of C plus the probability of D? 0.5 plus 0.1 is 0.6 here. This is the probability of A complement. We just obtained it from the basic principles. We obtained it from the first principles to get the probability of A complement. We obtained A complement first explicitly, and this comes from A because A complement means not in A. A complement means in the sample space, but not in A. So everything else is not A and B. So it is basically C and D, and the same thing can be done for B and for C as well. And after we obtain those events, those complement events, we can get the probability of A complement, which is 0.6. The probability of B complement is just the probability of little a, which is 0.1 here. And the probability of C complement, we have noticed that C complement has B, C, and D. So the probability of B plus C plus D, 0.3 plus 0.5 is 0.8 plus 0.1 is 0.9. That's why you see 0.9 here. So we have obtained the probability of the complements from the basic principles, from the first principles. Do you notice something here? What was the probability of A? 0.4. What was the probability of A complement? 0.6. So basically 0.6 is 1 minus 0.4. Also 0.1 is 1 minus 0.9, and 0.9 is 1 minus 0.1. We obtained these values without having this in mind. But is this a coincidence? Is it always the case that probability of A plus the probability of A complement is equal to 1, 0.4 and 0.6, 0.9 and 0.1, 0.1 and 0.9? Is this a coincidence? No, it's actually not a coincidence. That's always the case. And if we knew that, or if we noticed that, we could have obtained the probability of these complements easier without having to get these A complement and B complement events explicitly. Probability of A complement is always 1 minus the probability of A, and the probability of B complement is always 1 minus the probability of B, and the probability of C complement is always 1 minus the probability of C. So 1 minus 0.1 is 0.9. Now that's in the axioms of probability, and we will come to it in a couple of minutes. So the axioms of probabilities. The axioms of probability are the most basic rules that apply to any probability assignment. Let's continue with this example because we're also calculating some other stuff. So imagine that we need to calculate the probability of A union B. A is given, B is given. What is A union B? Since the events are given explicitly, we can just calculate the union of these events. Union means is contained in A or in B, so in both. So A is in the union, B is in the union, B was covered already, C is in the union, and D is in the union. So A union B contains everything, A, B, C, D, which means that the probability of the union is the sum of these values, which is equal to 1. Now, we noticed something here. By coincidence, A union B was the sample space. A union B was the sample space. Is it a coincidence that the probability of A union B is 1? It's not a coincidence. The probability of the sample space itself is always 1, and we will see that in the axioms as well. So let's wait until we get there. Now, finally, the intersection. What about A intersection C? We are interested in finding the probability of A intersection C. In plain English, what is the probability that A and C happen at the same time? That these events, A and C, happen at the same time if you do the random experiment. A intersection C, we can get it easy as well. A contained A and B, C contained D. So what is the intersection between this event and that event? Do we have anything in common? Intersection means belongs to both at the same time. We don't have any outcomes in common. So A is only here, B is only here, and D is only here. So A intersection C is actually the null set. A intersection C is equal to the 0 set or the null set. So the probability of that is equal to 0. The probability of A intersection C is equal to 0. So enough with this example, and let's move forward with the axioms of probability. What do we want to say here? We want to say the following. We have a random experiment, and the random experiment has a sample space, and the sample space contains outcomes. Each one of the outcomes has a probability. This is what we call a probability assignment, like the probabilities that are assigned to each outcome of a random experiment. What are the main rules, the most basic, the most fundamental rules that applies to the probability? First of all, the probability of the sample space is equal to 1. The probability of the sample space itself, so the sum of all probabilities in the sample space, is equal to 1. You know, probability equal to 1 means for sure. And we know, of course, if you do the experiment, we don't know which one of the sample space will happen, but definitely, for sure, something out of the sample space will happen. So let me try to give you an example here. Imagine that we toss 2 coins and we observe the outcome. So the sample space contains heads, 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 tails, tails, heads, and tails, tails. If you do the experiment, like if I give you 2 coins and I ask you to toss them, we don't know which one of them will happen. However, for sure, one of them will happen. So that's why the probability of the whole sample space is equal to 1 here. Each one of them has a probability of 1 over 4. If we add them up, it gives us 1, and that's always the case. The probability of the whole sample space is equal to 1. Now, the probability of any event in the sample space, you know, the event is a subset of the sample space. If the sample space itself has probability 1, then the event has a probability between 0 and 1. So any probability any probability is always between 0 and 1. The probability is impossible to be negative. It does not mean anything. It does not make sense. And the probability cannot be more than 1. It also does not make sense. So the maximum value for any probability, whether it's an event or even an outcome. So if you talk about the probability of these outcomes, like the probability of that outcome or that outcome if you roll a fair die, these probabilities are never less than 0 and never more than 1. So it also makes sense. It's very intuitive. It makes sense. Finally, the third axiom of probability says the following. In our sample space, imagine that we have two events, E1 and E2, that don't intersect. So E1 intersection E2 is empty. We have two non-intersecting events. Again, let me try to give you an example. You take the course. It's a random experiment because it's not guaranteed. Typically, it's not guaranteed what to get in a course. Maybe some grades are more likely if you're an excellent student, and you all are. If you're an excellent student, then the probability of getting an A is maybe higher. However, it's not guaranteed. So let's define two events. E1 is the event of getting an A. E2 is the event of getting a B. Now, if you take a course, can you get an A and a B at the same time? No, it's either this or that. So these two events obviously don't intersect. In other words, their intersection is the empty set or the null set. So the axiom of probability says if we have two non-intersecting events, then the probability of the union of these events is simply the sum of the probabilities. Let me try to give an example here. You take the course. This is our random experiment. You take a course, random signal theory, and let's say you are an excellent student. So from our previous observations, from our knowledge of the previous courses that you have taken, let's say we know that the probability that you get an A in any course is 0.7, and the probability that you get a B plus in any course is 0.2. And I want to ask myself the question, what is the probability that you get an A or you get a B? What is the probability of the first event union the second event? What's the probability that this happens or that it is simply the sum of these probabilities because they don't intersect. They don't have anything in common. The probability that the first or the second happens is basically the probability of the first plus the probability of the second. So in the example that I was trying to say, if the probability that you get an A is 0.7 and the probability that you get a B is 0.2, then the probability of getting then the probability of getting an A or a B is 0.7 plus 0.2, which is equal to 0.9. So the first axiom is that the sum of all probabilities in the sample space is always equal to 1. The second probability, any probability of an event or an outcome in the sample space is always between 0 and 1, never less than 0 and never more than 1. If we have two mutually exclusive events, we called this case mutually exclusive last time. If E1 and E2 are events that don't intersect, we call them mutually exclusive. Then the probability of the union between these two events is the probability of the first plus the probability of the second. Now, let's move on. So these are the most basic rules. If you have events that are mutually exclusive that don't intersect, the probability of the union is the sum of the probabilities. What about the probability of a union of general events that might intersect? So let's say A is an event, B is an event. Let's say A is the event that you get B plus or better. So A is the event that you get a B plus or an A. B is the event that you get a B or a B plus. So there is something in common. That B plus is in both events. And we would like to get the probability of the union. We cannot apply the axiom, so we cannot simply add the probabilities, but we say that if A and B are general events that possibly intersect, then the probability of A union B, it's a rule, it's a formula. The probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. So this is like our first formula here, the probability of a union in the general case. It's not necessary that A and B are mutually exclusive. It's not necessary that A and B don't intersect. If they don't intersect, then this term is equal to 0. Obviously, if they don't intersect here, it means that the intersection is empty and the probability of the intersection is 0, which means we go back to our axioms. Now, Is this clear? Is it intuitive? Actually, not so. It needs a proof. And that's why I have my own notes here. We can actually prove this formula either intuitively, so we can have an argument which is not rigorously mathematical. However, it's a clear, nice, and intuitive argument. And let's start with it. In addition to that, we can also have a rigorous formal mathematical proof that uses the axioms. So the only thing that we know is the axioms. Can we start from these axioms and prove this formula? Yes, we can. And I will try to talk about that in the next couple of minutes. So let me start first with the intuitive proof. Now, this is event A and this is event B. And as you notice, there is an intersection between them. And I'm interested to find the probability of the union. The union contains everything, A and B. Everything in A or in B or in both. So this is the probability of the union. Now, intuitively, it's not rigorously mathematical, but intuitively, if I add the probability of A plus the probability of B, how many times did we cover this intersection, this area in the middle? How many times did we cover it? Probability of A plus probability of B. It's covered twice. So that's why after we add A plus B, we have to subtract one intersection because this needs to be covered only once. I think this is a nice intuitive proof. Students usually like that. So intuitively, I think it's easy to convince ourselves that the probability of the union is the probability of A plus the probability of B, but however, minus the intersection of the two because we need to cover this only once. In other words, when we obtained the intersection, do you still remember this example? Imagine that we have A here, event A, which contains A and B. Event B contains B, C, D. What is the intersection between the two? The intersection contains only B. A is in only one, it's only here. It's not there, so it's not part of the intersection. B belongs to both. It is part of the intersection. B is already covered. C and D are not in the other one, are not in event A, so they're not part of the intersection. So in short and in summary, capital A intersection capital B contains only event B, and it's contained only once. It's not contained twice. It's contained only once. So this is what I wanted to refer to. And let me go back to our probability of the union and our proof. So this is only an intuitive proof. Can we have also a rigorous mathematical proof? Yes, we can. And let's have a look at that. The same setup. So we have a random experiment in the background. We have a random experiment that has a sample space represented by this big set that looks like a box. So this is the sample space. And we have two events, A and B. Now, what was the union? The union was everything, A or B. What was this red area here? It represents A intersection B. So in between here, the outcomes that are contained in both at the same time is the intersection. Do you still remember the set difference? That green shaded area here, that green shaded area, what does it represent? It represents A but without B. We say A minus B, or the set difference between A and B. This is the green area, which contains everything in A, but without the common part, without the intersection. Now, imagine I would like to express A union B. A union B contains everything, as we know. How can we express A union B? Isn't it true that A union B is A minus B, that green one, that green area, which is A minus B, union with B itself? Do you see the B circle? Do you see the B circle here? The B circle. If we do a union with the green area, it gives us A union B. You might ask me, why am I doing that? A union B looks nice and clean. Why did I express it in such complicated way? However, it's still true so far. It's still true. A union B, which contains both circles, is the A minus B area, the A minus B set, which is the set difference A minus B, the green shaded area, union with B itself. I think it's clear because what I just said here, what I just expressed here covers A union B. So what is the advantage of doing that? The advantage of doing that is that these two events, A minus B and B, if you look at A minus B here, the green shaded area, and if you look at B, they don't intersect. So A minus B and B are mutually exclusive, which means we are allowed to add the probabilities from the axioms. So if I'm interested to find this probability of the left-hand side, probability of A union B is the probability of A minus B plus probability of B, and this is correct, 100% correct, 100% mathematical because it comes from the axiom. However, I'm not done here because at the end, we need to express the union probability in this way. We have now the probability of the A minus B set plus the probability of B. That's why I'm doing something similar. So let's call this equation 1, and let's do something similar for A itself. Do you see A, the A circle? How else can we express the A circle? Isn't it true that the green area union with the red area gives us A? It's true. So we can say that A can be expressed as A minus B union with A intersection B. A minus B, the green one, union with A intersection B. Again, you might feel that this is strange. A is nice and clean. It's just A. Why did I express it in this complicated way? Simply because these two components, A minus B and A intersection B, the A minus B and the A intersection B, the green one and the red one are mutually exclusive. This green area here, the green set and the red set, they don't intersect. They don't intersect. So we are allowed to apply the axioms. So we can say that the probability of the left-hand side A, the probability of A is the probability of this event plus the probability of that event. So the probability of A minus B plus the probability of A intersection B. Let's call this equation 2. Simply substituting 2 into 1 gives us what we want. So if I go to 1 again, probability of A union B on the left, let's leave it as it is. Probability of B, let's also leave it as it is. But probability of A minus B, let's substitute from 2 here. Probability of A minus B is simply the probability of A minus the probability of the intersection. When we substitute here, we are readily getting the probability of the union. So what you have seen from here onwards is a rigorous mathematical proof for the probability of the union. In our course, I will not ask you to do proofs. However, we're still all engineers, and I cover many of the proofs because I want you to be convinced. It is not good that I just give you all these formulas without proof. No, we need to be convinced. We need to understand it makes sense. However, our course is based on problem solving. So our course is based on applying these formulas to solve problems. What you have seen here was a proof. So if you want to be convinced, perhaps you can just stick to the intuitive argument. However, if you can comprehend the mathematical proof with all its details, it is definitely a huge plus as well. Okay, let's take it from the probability of the union. We know that the probability of the union, probability of A union B, is probability of A plus probability of B minus probability of the intersection. Now, the special case, assuming that this is true, this is the probability of the union, and we have actually proved it. Now, if by chance, if by coincidence, A and B are mutually exclusive, they don't intersect, what happens to this last term? It becomes equal to 0. So what is the probability of the union in this case? It is simply the probability of A plus the probability of B. This is what we say here. So if A and B are mutually exclusive, then applying the probability of the union formula is probability of A plus probability of B, because the last term, the negative term, is 0 due to the fact that A and B are mutually exclusive. So what does this mean here? It means that we are going back. So if we start from the probability of the union and we say that this term is equal to 0 because A and B are mutually exclusive, we are going back again to the axioms. So everything makes sense and everything adds up. Finally, a couple of extra arguments before we finish this lecture. Probability of the union, however, extended to the case of having 3 events, A union B union C. Let's cover this without proof. However, we can do the proof in a very similar way to the case of 2 events. However, what I'd like to focus on here is the nice structure of this equation, so it's really easy to remember. The probability of A union B union C is the probability of A plus the probability of B plus the probability of C. And then in analogy to the 2 set case, we subtracted the intersection. So here we also subtract the intersection, but since we have three events A, B, and C, so we subtract all pairwise intersections. So we subtract the probability of A intersection B minus the probability of A intersection C minus the probability of B intersection C. So the probability of any two intersected. Again, probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C. So minus all three pairwise intersections among the three sets, but at the end plus the intersection of all three events plus probability of A intersection B intersection C. So let's cover that without proof because the proof would be tedious, a little bit tedious in this case. And finally, we also extend the concept of mutually exclusive. If we have only two events, E1 and E2, we have only two events to begin with. If we have only two events, E1 and E2, what is the meaning or when are these events mutually exclusive? We say events E1 and E2 are mutually exclusive if E1 intersection E2 is the empty set. Now, can we extend this to more than 2, to 3, 4, 5, 10, 100 million events? So a collection of events. So a collection of events, E1, E2, E3, and so on until EK, for any K, is said to be mutually exclusive. So we call these events mutually exclusive if for all pairs of events, EI intersection EJ, so the intersection between any two is equal to the empty set. So if E1 intersection E2 is the null set, E1 intersection E3 is the null set, E1 intersection E4 is the null set, E2 intersection E3, and so on. The intersection between any two is equal to the null set. So basically, every two are not intersecting. That's when we call the events, all of them, so the collection of events are called mutually exclusive. What can we say? What can we conclude if we have mutually exclusive events? What is the probability of the union then? Probability of E1, union E2, union E3, and so on until union EK as an extension to the axioms. If we have mutually exclusive events, if you would like to get the probability of the union, we just add the probabilities. So the probability of E1 union E2 union and so on until union EK is probability of E1 plus probability of E2 plus and so on plus the probability of EK. So this is just a nice figure that gives you an example to this. Imagine that we have four events in a sample space. We have four events, E1, E2, E3, and E4. As you notice, these events, they don't intersect. So there is no intersection between E1 and E2 and E1 and E4 or E1 and E3. Any two don't intersect. So these events, E1, E2, E3, and E4, are mutually exclusive. In that case, what is the probability of E1 union E2, union E3, union E4? It is simply the summation, E1, probability of E1 plus probability of E2 plus probability of E3 plus probability of E4, and so on. So we are allowed to add the probabilities of events as long as they don't intersect. Let me stop here and see you next time. Assalamu alaikum wa rahmatullah.